Let's find out how we work out the parametrics for a hyperbola. Now, I've just drawn in one branch of the hyperbola there, and there's my random point, but we want to get it in terms of a parameter, one measure. Again, we're going to use the auxiliary circle, so x squared plus y squared is a squared. But how do we find a connection between our hyperbola and this circle? It's an interesting way we do it, but this is how we do it. We drop a vertical down. Okay. Now, from that, we draw a tangent to the circle. And then from where the tangent meets, which of course will be perpendicular to the radius, we join the centre, and that creates an angle. And then as P moves along the curve, that angle will change because the position will move around the circle. Okay? So using that, the x value of our point becomes the hypotenuse of this right angle triangle here, which has a radius of a. So x over a would be the secant of theta, so x becomes a sec theta. Now, how to work out the y value? Some of you might think this is a little bit of a fudge, but this is how I work out the y value. Well, I know it's on the hyperbola, so if I sub in a sec theta, I can rearrange it and get, oh look, y is b tan theta when we play around with that one. Thus, it's got to be true because, amazingly, if I now substitute both into the equation of the hyperbola, it'll work. It's truly amazing. Okay, so there's our parametrics. A sec theta, b tan theta. All right, so how do our equations turn out? Now, very similar to the ellipse in that the equation of the tangent has that same form as the hyperbola. It would turn out to be x1 x on a squared minus y1 y on b squared is equal to 1. And the normal, again, on the right-hand side. You remember with the ellipse on the right-hand side, the normal went a squared minus b squared. Well, with the hyperbola, it becomes a squared plus b squared. And again, I refer you back to that formula we looked at for finding eccentricity. For the ellipse, it was e squared is equal to a squared minus b squared on a squared, whereas for the hyperbola, it was a squared plus b squared. So in other words, they both equal a squared e squared. But again, it's usually easier to go a squared plus b squared, because if all I got is the equation of the hyperbola, I don't know what the eccentricity is yet, but I do know what b is. In parametric form, it becomes x sec theta on a minus y tan theta on b is 1, and for the normal, ax on sec theta, by on tan theta again equals a squared plus b squared. But of course, in order to find these, we are going to have to differentiate sec and tan. Now, tan we've dealt with, sec we haven't. Way I could easily prove this, sec is the reciprocal of cos. So I could say, oh, how do I differentiate 1 over cos? Oh, minus the derivative on the function squared. Turns out it'll become sec tan. Okay? So differentiate the angle, that goes out the front, and then it's sec tan. Again, the angle does not change. So differentiate sec, you get sec tan. Tan, of course, we've seen. Tan becomes sec squared, you remember. Okay. Chord of contact. Just like the ellipse, it will also mimic the equation. So it will turn out to be x naught x on a squared minus y naught y on b squared, where x naught y naught is that external point. Ta-da! And you thought I was lying when I said this was going to be quick today. There you go. Pretty much it's all the same sort of stuff, but now we're dealing with the hyperbola instead of dealing with the ellipse.